Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon, everyone. It's my great pleasure here to have Mark Maimon here with us today. And he'll be basically talking about the Mars Curiosity rover. He's been at JPL working on rovers and autonomous robots for space for a very long time. And I'm really excited to hear more about this today. Mark.
So I'd like to talk today about what drives curiosity. I'll explain some of the robotics technologies on the Mars Science Laboratory, NASA's current Mars rover. We landed about 2 years ago. We landed in August 2012, and we've been operating on the surface of Mars for that long. And we share a history with earlier NASA rovers. The current one is the big one on the right, is Curiosity. And the one next to it is the Mars Exploration Rover. So we had two of those, Spirit and Opportunity. Opportunity is still working today. The 90-day mission has gone on for more than 10 years so far. And then at the bottom you can see Sojourner. Sojourner landed in the 90s. That was the very first NASA Mars rover. And that was supposed to last for a week, and that ended up lasting for 3 months. So we tend to run over our specs, which is a little bit of a problem, but it's working out pretty well for us. So I want to talk about how do we drive these rovers in a few different aspects. So one thing that drives Curiosity is the people that work on it. So I've shown some pictures of some of the people who are the human rover drivers who get to send commands up to the spacecraft. And you can also see one of us working in the test bed, and that gives you a sense of scale of just how big this vehicle is. It's a rather large vehicle. The wheels are each 50 centimeters in diameter. So they can climb over larger rocks than the previous ones could. And you'll see some more of that in the talk coming up. But basically, when we're driving these rovers, we're sitting at a workstation, pictured here, and we're reviewing pictures, either 3D reconstructions shown on a mesh, or we're wearing the stereo goggles so we can tell what the world looks like by looking at pictures taken from the stereo cameras on the rover. We use both of them because you need the 3D model to simulate your drives, and you need the human eyes to really get the feeling of what the terrain is. You really get a good feeling for where there are depth discontinuities, ridges or something by looking at it yourself. Yes?
What's the range of round-trip times for communication?
Good question. The range of round-trip time for communication depends on where the planets are. But it's between 4 and 22 minutes, depending on whether the planets are close by or opposite. Actually, that's one way. So round trip would be 8 to 44 minutes. And a lot of people think that that's the real limitation in operating the Mars rovers. And it is a physical constraint on operating the rovers, but that's not the only problem we have. We also have the constraint that we are sharing the deep space network. We communicate with the rovers using these big 70-meter or 35-meter antennas. And a lot of people want to use them. We have dozens of space missions, and they all want to share this limited resource. So for the Mars rovers, we get to talk to the rover by sending commands really just about once a day. And we get data back a few times a day, 2 to 4 times a day usually. And we usually get the high priority stuff first, and then we transmit the rest as bandwidth allows. But that's really the limitation, is the logistical use of the communication platform. And it kind of works out pretty well, because what we end up doing is spending a whole day of humans creating a plan, reviewing it, making sure it meets the resource constraints, simulating it, testing it, reviewing it with everyone, and then we'll send it up. Then we go home and go to sleep, and we wait for the next results to come in. When the rover's done executing it, it'll send the results back, and we can review what happened and get ready for the next day's activities. So the way that we operate it is, as I was mentioning, we look at the images we get. Now this is from Earth. This is from our test environment, our Mars yard. And the rover will take pictures that look like this. And this is kind of what you would see if you were standing there, because the mast is at about human height. It's just under 2 meters tall. And so we can either review pictures or we can review the 3D geometry over there. It's just a still frame, but that's actually a 3D mesh. And we can zoom around and move it and watch the rover drive across it too. And so what the human drivers will do is look at whatever images have come down to see what's available in the terrain nearby. And then we'll plan some activity on the rover. So this is showing you the plan for one day on Curiosity. And you can see we intended to go in sort of two short segments, one straight segment, little turn, and then another segment. And you'll notice that the camera's going to start moving pretty soon. It's showing you which way the camera's looking. So that motion goes on when the rover is being asked to drive itself autonomously. We're asking the rover to turn on the cameras, see what's out there, and only drive if you think it's safe enough. Find a safe path through the world ahead. And this view of the drive, I'll just play it back again. This view of the drive is what we simulated, is one possible way it could execute. But when we actually send the command, it'll depend on what it sees in the terrain that'll determine what it does for that second half of the drive.
You're saying the first half is not autonomous?
Right, yeah, the first half is actually what we call directed driving. And so in this case, humans have spent 8 to 10 hours looking at the terrain, studying it, reviewing it, talking over with the science team whether it's the same kind of material we expect or how we expect the rover to behave. And it's always faster to just tell it to go, just like a remote control car, like go forward 10 meters, stop, turn a little bit, go forward 5 meters, stop, turn, without using vision. Now, even in this directed mode, it's always doing onboard sanity checks. It's always making sure the motor current doesn't get too high. We'll always set limits on how much tilt we expect during the drive. So if it finds itself at too much of a tilt, it'll autonomously stop motion. We have dozens of those kinds of checks running all the time. But in terms of using vision to make an autonomous choice about where to drive, yeah, when that is turned on, it's a much slower driving mode because we have to stop, take the picture, process the image, make the decision, and then execute it. So that takes more than tens of seconds. So we don't do it all the time. As a robotics researcher, I wished we would have done it all the time, but the system just wasn't up to speed enough. And in order to get the best overall drive distance out of the vehicle, it's cheaper in terms of Mars power and resources to have humans spend 8 hours doing the planning, and you get an extra 60 to 100 meters out of it that way. Yes?
When Curiosity landed, we heard about how you drivers have to live on a Martian day. Do you still have to do that?
Yeah, do we have to live on a Martian day or a Mars time? We did when we landed, you're right. So for about 3 months, we're living a Martian day, which is about 40 minutes longer than on Earth. So when the MER rovers landed 10 years ago, as a single guy with no kids, I loved it because every day I could sleep in 40 minutes longer. 2/3 of the time, I go to work, there's no traffic, parking is really easy. But now it's a little harder. And so most of the team doesn't want to do that all the time. And so what we do is, when we first landed, just to make sure we get everything going, we do live on Mars time. But after a couple months, we go back to Earth time. And what that means is we won't be able to interact every Earth day with the rover. You can make a plan, but you won't get the results of it for 30 hours. So you may not get it until after the next workday has happened. And so we just plan activities for that time that don't require us to know where it is or what happened on a previous day. But yeah, so we don't have to do that anymore, thankfully. So another aspect of how we drive it is how far ahead we can see. And this is an example of a terrain mesh. So stereo image views of the terrain around it reconstructed into 3D shape. And when we see enough terrain data in 3D, then we can make a choice to drive in this directed mode into it. Right? When we see the terrain, we understand it, the geologists tell us what it's like, and we know that there's nothing missing, there's no uncertainty about what's out there. Then we can just send it out onto that terrain. We also have a good understanding of just how much the vehicle's likely to slip. And so if it's at a high tilt, it'll slip more, so we wouldn't command it to go very far at a high tilt in the blind. We'd always have it check. But anyway, this gives you some idea that as you get farther out, you get less knowledge about the terrain, and that's really the constraint on how far you can send it in a directed way before you have to turn on the autonomy to take over and figure out where it's safe to keep going beyond where we can see. So another view that we have into Mars is we get these grayscale stereo views that give us a nice 3D knowledge of what's nearby. We also have science cameras on board, the mass cam, and they're good color imagers, so we can see farther away with them. So this isn't a stereo view, it's just a monocular, but we can actually zoom in at pretty high resolution and get a good feeling for what's coming up even beyond where we can see in stereo. So we may not know the shape of the terrain, but we'll at least know, is it rocky, is it sandy, does it look like there are gaps there? So we have different ways of looking at it, both from the rover and even from overhead orbital views. And I really already reviewed this one, so let me just skip on here. Curiosity will carry out the activities that we send once a day. It'll receive the commands early in the Martian morning, or like 9 or 10 o'clock in the morning, and then execute as much of the plan as it can, as well as it can. And in mid or late afternoon, it'll send the results of the day to the orbiters. We have 3 spacecraft orbiting Mars right now that we can use for relays. Usually we use the Mars Reconnaissance Orbiter. There's also Mars Odyssey, and occasionally we even get to use Mars Express. So it's always better to use the relay stations rather than talk directly to Earth, which we can also do, because we get much more bandwidth. Very slow talking direct to Earth. It's like a 14.4 modem. It's really, really bad. But when we use the orbiters, we're able to get on the order of about 500 megabits per day of data back. That's sort of one nice YouTube video, basically. Yeah.
So can you describe the technical reason why that's the case?
So why is it the case that we're so limited? Well,
Why do you get more bandwidth from using the orbiter?
Right. So the orbiters give us more bandwidth because they have bigger antennas, and I don't actually know the power situation between the two of them, but really just the larger antenna gives it more opportunity to send a better signal back. And perhaps it's due to the more visibility, but I don't actually, I'm sorry, I'm not a telecom engineer, so I'm not sure. I just know that when we get the data from the rover, it trickles in very slowly for a long time and never reaches as much as we get in sort of a big burst from the orbiters. So it's also maybe just, that's the main reason. It's just the orbiters are so much closer to the rover, it's just a couple hundred miles to send a signal up to the orbiters, not millions of miles or hundreds of millions of miles. So the antennas on the orbiters are better able to send back the extra bandwidth. Was there another question? Or?
What is the bandwidth you mentioned?
What is the bandwidth I mentioned?
Yeah.
I said 500 megabits per day.
That between the orbiter and Earth, or between
Orbiter and Earth, yeah.
And
Well, for this mission, only for the Mars rover relay purpose. They also have their own data, and they could relay for other missions as well, like the Opportunity Mars rover.
what are the bandwidth between Curiosity and the orbiters?
I don't actually know. I'm sure it's less than 500 megabits, but I don't know exactly, because we have multiple passes. It's not just once per day. But I'm sorry, I don't have the number directly. So I showed you that we like to rely on information collected by the rover, the pictures that the rover has taken, because they're the highest resolution, they're the most current, they're the best localized information that we have. But we also have images from orbit that were taken either pictures or in multispectral bands. And so the science team will use all this information to help us plan our long drives. The science team is who chooses where we're going and what the destination is. And they help us tactically by explaining to us ahead of time, this terrain looks like it's pretty rocky, this terrain looks really sandy. They'll give us those inputs, and that helps us determine what our best choice is to get to where they want to go. On a given day, we'll only go between anywhere from a meter to over 100 meters. I think our record so far is over 140 meters. You'll see that coming up. But the mission overall has gone so far over 9 kilometers in 2 years. Do you have a question?
Well, this is a very naive question, but if so much is dependent on how far you can see from the camera on top of a 2-meter mast, it seems like it wouldn't be that hard to have a telescoping mask that goes up 5 meters or something like that, just to get you, just to put, I know it's not there now, but
Right.
next time.
Right. So I think the question is, if we're limited by the height of the mast, why not go higher? Why not have a telescoping mast, something like that? Yeah, that's an interesting idea. You're right, we don't have that today. Basically, building any space mission, the more moving parts you have, the more likely things are to break. So unless it's really going to benefit the mission tremendously, they're not going to want to do something like that. You know, we do have the orbiter information, and we can see the surface at a really good resolution. It's like 1/4 meter per pixel, 25 centimeter pixels. So that's pretty phenomenal. The problem, of course, is just keeping it current, knowing where the rover is on any given day. But yeah, you're right. So having a camera up higher would be nice. You know, having something floating above you would be nice to look down. Yeah, that would definitely help us be able to drive in a directed way for a longer distance. Yeah.
Maybe we're going to mention this later, but we're curious to know if is the robot also doing some local mapping, so taking all the scans and building up over time, you know, a larger model of the area it's in, so that it knows when it comes back to the same spot, that sort of thing.
Right. So is the rover building its own map and doesn't know when it gets back to the same spot? It can do that. When we turn on a capability, I'll show you in a little bit, then it can build a map and have that knowledge. It doesn't do self-registration to that map, though. That's not a capability that we thought we needed to have on board. We do get to talk to the rover once a day. And so after it's gone some distance, the humans on Earth can figure out what the localization is and go from there. It would be, that would be a nice capability. We have shown the ability to drive more than one day in a row. And so for that, the better your registration, the better you'll be able to identify any problems from orbit. But so far, we haven't done that often enough that they've wanted to put that capability on board. Yeah?
How often does the terrain change due to winds or whatever things?
How often does the terrain change?
Yeah, so during the communication time, the thing
Oh.
will change.
Oh, does the terrain change like in between the time we talk to it and it goes again? Not normally on that scale. There was a recent exception to that. The Opportunity rover recently did some work over a few days, and the next time they took a picture, they had discovered this new rock right in front of it that wasn't there before. And it was a big deal. Everyone was kind of shocked where this thing came from. Was it a meteorite? Who knows what it was? And it was perfectly timed because it was on the 10th anniversary. It was just before that. So, a mystery for the 10th anniversary. As it turned out, they discovered that they had dislodged a part of the terrain uphill when they were turning in place a few days earlier. And it just ended up rolling down to the spot where it came to rest afterwards. But, I mean, to answer more generally, no, the terrain doesn't usually change on a scale that we can notice, overnight. We do check for that because, especially if we're using the arm to do any operations, you don't want to discover that you've slipped downhill all of a sudden. So we do these slip checks. We take images and we compare before and after to make sure that we're still in the same place. And the rover can do that autonomously on board. So it can do it from one position to tell if it slipped. So this is just to show you the overall path that we've taken so far. This is current as of a few months ago, 4 months ago, but we landed up in here. And we only drove a relatively short distance, less than 1 kilometer. And the science team was ecstatic to be here because this was the junction of 3 different types of terrain units. And they discovered that coming down here was like water outflow. We're talking billions of years ago. And so they're able to determine by analyzing the minerals and the contents of the rocks here that this area used to be covered, at least partially, with normal pH water. Earlier rover missions had found evidence for past water that was highly acidic. They found minerals that only formed in very acid environments. But here, for the first time, Curiosity found the evidence for water with a neutral pH balance. In the press conference, I think the science lead said you could take a cup and drink it if you were around a few billion years ago. What's that? Until you say, yeah. So anyway, we spent a long time here, and then we really picked up the pace and started driving down, and we've since gone farther than this, off of this map. You can see the scale here this is 1 kilometer. And I'll show you the odometry later. We've gone over 9 kilometers so far. So what else drives Curiosity? A lot of what drives it on board is robotics technologies. So I've listed some of the things that we have for helping us operate the vehicle so that we don't just joystick it all the time. We can rely on extra capabilities to go farther or go more safely, go more robustly to where we're going. We have very basic drive responses, spinning the wheels with velocity controlled driving. I mentioned earlier different autonomous fault responses. There's a half a dozen kinds of vision-based autonomy that I'll get into. And we have an arm on board and instruments on the end of the arm. And other robotics technologies that lead into it include simulation, simulating the activities of the arm, and you'll see some of that, and validating our sequences before we send them up. Sorry, there was a question.
So when you said joysticking it, I'm assuming that you generate the commands locally, and the commands are sent to the orbiter, and the orbiter relays them to the...
Yes, I apologize. I shouldn't have said joysticking it.
So now there's a big delay in all this.
Right.
And so do you have local simulators with 3D terrain mapping that you actually test it out before sending the commands?
Yes, and that was what we saw earlier, somewhere here. Right, so this, okay, yeah, so this slide is showing you an animation of a planned series of drives. So when I said we joystick it, what I meant was we log a series of commands into a control sequence. We simulate the sequence, we review it, we confirm with the science team it's the right thing to do. But by joysticking, I just mean we're not, I shouldn't have used joysticking. I meant directed driving, where we're not using vision on board for the vision to adjust the path that it's taking. The first part of this path here is not using vision. It's just being commanded to drive for some distance. And then at the midpoint, you can see where it changes direction. The simulation showed the camera moving around. And at that point, it is being commanded to use its vision to autonomously determine, is it safe to go this way? I want to go over here, but you, the rover, get to choose how to do it, because I want you to be safe.
Question.
Yep.
How much distance could it cover if it was in direct drive for the entire day?
How much distance
So
could it
basically,
cover?
how fast is it at raw speed?
Oh, what's the top speed? We can spin the wheels at up to 6 centimeters per second. We usually spin them at 4.2 centimeters per second, but we often pause in between. We don't want to just run the motors continuously. So it can be achievable that you could get over 150 meters an hour, but we normally get closer to about 100 meters an hour. That's sort of our blind speed, usually. And just by practice, our convention is that we won't ever drive 100 meters in the blind without stopping to check and see that we're not stuck, because we did that on opportunity. And back in April of 2005, we commanded a 90-meter drive without looking, and we got stuck after 40 meters. But the wheels kept spinning for another 50 meters, and it ended up digging itself into a dune we ended up calling purgatory, because it took us 2 months to get out of it. It took 2 weeks to get disembedded from the meetings discussing what to do, and then the rest of the time actually getting out of the sand pile. Because of that, the drive rate is even a little bit slower, more like 80 meters an hour, something like that.
So is the terrain, is there a lot of loose terrain, so sand, pebbles, the kind of things that would make you talk of slipping a number of times, right? Is that right? The robot slips because it's not solid?
Yeah, so is there a lot of slippery terrain and loose sand? And yes, there is. And we'll see some examples of that coming up. It is interesting, though. We tried sending Curiosity recently. We've been experiencing a problem with the wheels, that the wheels keep getting poked through with some of the rocks that are embedded in the soil there. And so one of the solutions was going to be, well, let's drive on sand instead, because there's this whole sandy area. Let's try that. We tried that, and we started getting embedded again. So that turned out not to be a great solution. But yeah, basically there are all kinds of terrain. There's sand areas. There's exposed bedrock. The terrain we like the most is something that has sort of loose sand around, or something that we can push rocks into the ground, as opposed to rocks that are cemented in place that poke into the wheels. I'll get back to that. I'll show you several examples of that. So now, I'd like to just show you some of what the hardware is on the vehicle. So start with the arm. The arm on Curiosity, it's 2.5 meters long, and the arm here actually weighs more than the whole MER rovers did. It has a really heavy and well-instrumented turret on the end. It's a big wheel, spins around, and has different instruments on it.
Kilos Earth gravity or more Earth?
Well, kilos is the same on both. It's a mass unit. The Mars exploration rovers, had a comparable mass. Things weigh 1/3 as much on Mars as they do on Earth, but they have the same mass. So here, the arm and the payload is, I think it's over 10% of the mass of the whole rover. And we use the arm for a lot of different activities. Some of the science activities require direct contact with the target, with the rock or the soil. So we have to place the arm or the turret onto the surface. Other things we can do remotely. We have other instruments on board that can do remote sensing. But this arm is what we have for doing the placements. And right now, so far, this is the most complex manipulator we sent to another planet on a robot. This has a drill on it that we've never had on a robot before. Human astronauts have gone to the moon and used a drill to go subsurface, but this is the first time we've had a mobile drill platform that we can just place wherever we end up going. And we've taken 4 samples so far. This is a close-up view of the turret, some of the instruments on board. We have a high-resolution camera, color camera, the MOLLE, and we have a spectrometer, the alpha proton X-ray spectrometer. You place it on the instrument and leave it for some integration time, either just a few minutes or overnight for more detailed understanding. And it gives you the breakdown of what's inside the soil it's sitting on or the rock it's sitting on. We can scoop up sand in the terrain, and we can also brush sand off of rock surface. The scientists always want to know what's inside the rock. They don't really want to know what's on the surface. The sand has blown and weathered it on the outside, but to clear it off and get the best spectral readings, they like to brush it off with the brush sometimes. So the arm has a force torque sensor to measure how much pressure it's getting when it's being placed onto the ground. And that's used internally just as a safety check to know when to how much force to push down on to make sure you've got good enough contact and not too much contact, or you haven't lost contact. And you can see here some of the what's in the ARM workspace, things it can do with the samples. When it collects a sample, it can drop it into different instruments, into the inlet for the ChemIn or the SAM science instruments that can process the materials. We have effectively like an easy bake oven inside. It takes the samples and heats them up and analyzes the vapors that come off of it when it's been processed. In addition, we have another instrument on the mast that can shoots a laser. The ChemIn instrument shoots a laser out, vaporizes some material some distance away, and again uses a camera and a spectrometer to analyze the vapors that come off. The rover has several calibration targets on board just to keep the instruments, have a good understanding of how the instruments are working. So we got color cameras, microscopic imager targets, calibration targets for all the different spectrometer and imaging sensors there.
Is that a penny on Mars right now?
Yeah.
That's what that is.
Yeah. Actually, a penny on Mars right now. And so that we can send the arm to places on the rover itself. It has its own teach points, like places we know where it's going to go. Part of the checkout activities were to make sure that it's going where we expect, and we can measure that with fiducials on the arm to guarantee that we can predict the effect of Mars gravity on the arm very well. Normally when we operate the arm, it has sort of a sweet spot where it has the best behavior, where it's able to get multiple orientations and has the best known precision in measuring the surface using the stereo cameras. So we call this the magic cylinder. So we generally like to put targets into this this volume if we want to put the instruments on it. That's our goal for a drive, is to end a drive so that the target is in here. That gives us the best opportunity for getting the instruments on it. If we don't succeed, it can still work outside of this volume, but it's much more constrained. We may not be able to successfully place on that target without further positioning the vehicle. And every time we position the vehicle, that's another day that it takes to send a new command to drive and confirm that it's there before we can do more arm work. So here's an example from our simulation program of an actual command sequence that was sent up on Sol 612. That was maybe 4 months ago. And what you're seeing here is what the rover planners would see in the control room on Earth as they're planning the day's activities. You know, we have a model of the terrain in 3D, and we can watch what our commands will do on that terrain. And it does interact with the virtual terrain in some cases. In other cases, it doesn't. So you may see like the instrument go into the ground. And what that means is just that if it doesn't know that there's a surface there, it'll just push it through. On Mars, what's going to happen is it will contact, and you'll get a force feedback on it. But that's not always shown in this simulation. But we use this simulation to make sure that when we take pictures, they line up where we expect them to be, that we're on the right target that the scientists want. This animation is created and visualized throughout the day by the rover planner, and at several strategic meetings throughout the day by the whole science team and the whole operations team. So everyone has a chance to see this, see the plan, review it, make sure we're hitting the right target. You know, anyone can say at any time, wait a minute, don't you want to go to that other target over there? Or how are you sure you're not going to be able to, you're not going to slide off if there's a pebble nearby, something like that. And so this visualization really makes it possible to get this all done in a single day without having to do additional thinking or extra tests by doing anything on Earth in reality. We really use the simulator almost exclusively. We almost never go back to the actual test vehicle because we never know exactly what we have on Mars, right? It would take us a while to try and reconstruct everything in reality. We just use the sim for all of our planning. So we can use the arm to do contact science, and this was the first rock that we used for which we did that on the Curiosity mission. And this is what it looks like from the top of the deck, from the navigation camera. As you can see, the arm is reaching out and stretched out, placed onto the target here. And these are some of the images that were taken during that close touch. So another thing we discovered we could use the arm for is self-inspection. We could take selfies with the arm. You reach out and just look back at yourself. And we did that to look at the belly pan, look at the wheels under the rover. And we've also done that to get this whole selfie image here. Now this has become an iconic view of the rover, but it actually took a lot to generate that. This is going to show you an animation of all the motions that the arm had to go through in order to collect those images to be stitched together on the ground. And also you'll see the view through the camera as it goes. So this wasn't something we had planned originally, but after we landed on Mars, some of the team said, you know, this would be really useful to be able to see back at the vehicle. And so they worked this up in simulation, and then went out to our test model, tried it on the test model, and were able to generate actual images that our team could then, stitch together and co-register to make the overall view. So the other kind of technology that we can do with the arm, another thing we can do with the arm is to sample sand with a scoop on the arm. A scoop isn't a new instrument. We've had that on earlier missions. Even Viking, I think, had a scoop, and the Phoenix mission 8 years ago also had a scoop on it. But that's another resource for us to get some sample into the system. So we can either scoop or drill. And here's a close-up of the drill bit as seen by a camera on the rover. So anytime we use the drill, we can use the cameras to get the close-up view to see just, does the bit still have enough life in it? Is there anything stuck on it? We have extra bits that we can swap out if we need to, but happily we haven't needed to yet. And you can see the end result of using the drill is that we really pulverize the material. We create this powder. And what happens is so the drill sits on the terrain with these two prongs, and then the middle piece comes in and out and starts spinning around to drill into the surface. And once it drills down, it creates the powder, and the powder goes up. There's a helix in the middle here, and it just the powder slides up the helix into the unit. And once it's inside here, if we decide we want to keep it, we end up twisting the arm in through a series of maneuvers using gravity to send it through the system. It moves from here through a door into another sample container, and there's a whole mousetrap kind of configuration inside for routing it through different sieves to filter out different particle sizes and routing it to different storage places. Here's a video that shows you the drill on a rock on Earth. This is the engineering model. It's not a video from Mars, but you're seeing how the drill works in a time-lapse view here. And what's kind of neat is not only do you see the activity here, but you can see some sand particles pushing away at the bottom. And we see that on Mars too. If you look at the before and after pictures, you can see little pieces of the terrain, going downhill after the drill has been there. And just to give you an idea, the way we choose a target is we'll get the stereo view, and we'll also get this very detailed color view. And the science team will go and try and figure out, which way do we want to go? Which targets do we want to look at? What's our priority? And they work with the rover drivers to go between what the scientists think is the best target to what the rover drivers think is achievable. Because it may be an awesome target, but if you can't drive there and you can't reach it, it's not going to do much good. So we really work together. The science team outlines the goals, and the rover drivers, rover planners try to reach that goal. So yeah, I mentioned that once we collect a sample, it goes through the mechanism here. We have different sieves, different filters to prune them down to a certain size, and they end up getting portioned out into tiny little, like aspirin-sized tablets. And it's those tablets that get processed by the instruments inside to get baked or processed in other ways. Okay, so that was the arm. Curiosity also has cameras and mobility capability and technologies. So let me go through some of that. We have 17 cameras on the rover. So we have body-mounted cameras on the front and on the back. There's actually 4 cameras here on the front, 2 and 2 on the back. And there's 4 cameras up here. There are more cameras inside the mast. There's a camera on the arm. There's a camera in the laser scanner or the laser instrument. And all those can provide data for Earth, but on board the rover, the only cameras that it really uses on board autonomously are the body-mounted hazard cameras and the mast-mounted navigation cameras. And even though you see 4 here, we only use 2 at a time. We have a redundant backup computer, and the cameras are tied to a particular computer. So if you're on one computer, use one pair of cameras. If you reboot to the other computer, use the other pair of cameras. That's going to be a problem later on in this story, but that was the design. So we get a nice wide field of view. Here's a sample field of view from the body cameras. It's 120 degrees. It's a fisheye view. It's actually a 180-degree diagonal view. And we use those to detect nearby rocks and also look at where the arm's going to be placed. And here's an example from the mast. I mentioned you're at human eye height. These are the cameras that we use for those activities, and you can get a nice view all around the rover, looking out 100 meters or nearby too. And so what's some of the processing we can do with those images on board? Well, if we're not doing plane-directed driving, we have the option of several kinds of vision-based autonomy. So one option is that we can ask the rover to look for hazards around it, figure out where they are, and steer to avoid them. So that's what we call autonomous navigation, or autonav. So that's one way of driving. Another way we call visual odometry, and what that does is when you're driving your car, you have an odometer in your car, and it's measuring your distance, and it's pretty accurate because you have rubber tires moving on asphalt. They don't slip that much. We have metal wheels going through sand and rock at different slopes, so we slide a lot more. And we don't have any sensor on board the vehicle that can detect slip in real time. There's nothing there. You have accelerometers and you have gyroscopes, but gyroscope only measures your attitude change, doesn't tell you if you're sliding one way or another. And the accelerometer, in theory, you could doubly integrate it and get position information, but they're so noisy that you really can't rely on that. So what we do is we actually use pictures. We take before and after stereo pictures, and we can process those pictures to figure out the transformation of where the rover went, and that can be used to correct our position as we go. It's not on these slides, but we also are just demonstrating now a new capability for visual target tracking, visual servoing. You aim the camera at a target and ask it to keep watching it, and it'll keep tracking it as it goes by it. So for visual odometry, the way that works is we detect points in the nearby terrain automatically, just find whatever features happen to be there, and then track their motion across frames. So this is sort of a before and after frame. There's a rock here, you can see the arrows are pointing down this way, and the rock over here has moved down to that point. So those are just examples of different frames from actual motion on the vehicle. So this is a very helpful capability that tells you when you're slipping and gives you precise positioning, and we really couldn't drive through sandy or sloped areas without this. Yes?
So are you doing the tracking on Earth or on robot?
This is all on the robot. This is not done on Earth.
Program to the robot.
Right. Well, we have the software on the robot, and what the software will do is if we turn it on, it'll automatically start taking pictures as it drives, and then it'll stop every meter or so, whatever distance we tell it, to take another picture, compute the difference, and update its position knowledge on board. So it's able to use that to figure out.
I was thinking like computer vision advanced really fast in the past few years, and you just keep uploading new program there.
Oh, so if you're asking if the computer vision advances quickly, can you update the software? We do have the ability to update the software, and we do that sometimes. But the mission overall has a sort of a low tolerance for big changes. So we generally won't do huge updates unless there's some really big benefit to it. Because anytime we send an update like that to the software, we have to put it through a whole test program. We have to revalidate all the other software to make sure that's still working. We didn't break it accidentally. So we don't generally upload new stuff, but on MER they did that. Spirit and Opportunity in 2006 did get new technologies, like 4 new technologies uploaded, and that was done through a whole big test program. It took a couple of years to go through the test program, but they did get it done. Yeah.
So I'm guessing the operators cannot provide the equivalent of GPS or.
Right, yeah. You're asking whether the orbiters can provide GPS, and no, they can't. We don't have a MPS at Mars, no. I would love to have that. Having GPS equivalent on Mars would solve a lot of problems, but we don't have it. So we rely instead on this visual odometry of looking at the local terrain.
Has there been any discussion of creating a constellation to do that kind of thing?
Yeah, people have talked about making something like that, but the expense of putting enough satellites around there to support that is just beyond anything that we have so far in our infrastructure. It would be great, if we actually start putting things on Mars for real, for long extended periods, or people there, you're going to want something like that. But it's not available today. So I think I'd like to show a quick video here, just to give you an idea of how the safe driving software works. When we ask it to drive and avoid obstacles along the way, just want to show you how that capability is implemented. Now this is showing you the MER vehicle. It's really a very similar kind of approach on Curiosity, but Curiosity is using more pictures than MER did.
Class, today's lesson is autonomous waypoint navigation in natural terrain. This is your designated goal location. First, watch this video to learn how it's done.
A robot exploring natural terrain needs to continually find and avoid navigational hazards, such as large rocks and steep slopes. Our system models the terrain using stereo vision, determines and stores how safe the rover would be at each location in the model, then estimates the traversability of several possible driving paths. The rover chooses the safest path that moves it closer to its goal and drives a short distance along that path. This process of taking pictures, predicting rover safety, and driving continues until the goal is reached. The first step of the navigation cycle is to take pictures. A pair of cameras at the front of the rover captures simultaneous left and right images of the terrain. Features in the image pair are correlated and triangulated to determine the distance to the feature from the cameras. Range data must satisfy a number of tests before being accepted as correct. Confusing or misleading features, like parts of the vehicle and areas of the image seen from only one camera, are automatically removed from consideration. The resulting points are accumulated into a three-dimensional geometric model of the terrain. This 3D model is evaluated for safety across a grid at rover wheel resolution. For each grid cell, points within a rover-sized patch are fitted to a plane and rated for traversability. Each patch is checked for steps, excessive tilt, and roughness. Obstacles are expanded by the radius of the rover, so that the rover center will stay far enough away from the obstacle to keep the entire vehicle out of danger. Each patch is accumulated into a gridded traversability map that drapes across the terrain near the rover, including areas not currently visible from the cameras. A small number of paths are superimposed onto the map and evaluated both for safety and also closeness to the navigation goal location. The rover chooses the safest path that gets it closer to its goal and drives a short distance along that path. After each step, the navigation process repeats until the goal is reached, no safe path is available, or the rover is commanded to stop.
There's one last little bit. Give it a second.
Now it's your turn to try. Oh dear. Maybe we should watch that video one more time.
Okay.
Is there any significance of number 42?
I don't even remember. Where was the number 42?
Hitchhiker's Guide to the Galaxy,
What?
the answer to the ultimate question of life, the universe, and everything. And if everybody knows what the question is, the ultimate answer is, let me know, please.
Okay. Oh, that's probably the source. Yes. I did the screenplay for that, but I didn't do the animation. So the animator got to sneak his own little thing in there. Okay.
So you said that the pilots here use it and the rover uses it. So how often do they just make it autonomous and say go there, and how often are they giving it the exact path plan? Or maybe I misunderstood.
No, that's a fine question. Maybe I can jump ahead and answer it. So how often do we choose to drive autonomously versus not? This is a breakdown of all of our driving as of about 2 months ago, and it's broken down by drive mode. So the red on the bottom is the directed driving, where it's not using vision at all. It's just using the, following the commanded distance. And the purple on top is where it's using what you just saw, the vision to look at the terrain and figure out where the rocks and ditches and slopes are and avoid them. So it's maybe 10% of the time that we're using that autonomous mode. In my dreams as a researcher 20 years ago, I thought when you're driving on Mars, you'd want to use that mode all the time. It's the safest way to go, and it is. But it's just too slow. We wouldn't be. The total distance here is about 9 kilometers, and if we'd only driven in that mode, we'd be much less distance accomplished.
It's slower. Why is it slower?
Why is it slow? Well, it's slow because we have a 133 megahertz CPU, which I only get a fraction of the time on it, and it's slow because the cameras are not designed to take images very quickly. We actually have to stop, expose the images for half a second, transfer them across a camera board into the computer's memory. All that takes more than 10 seconds for a regular stereo pair. So it's just not built like a terrestrial vehicle with fast image acquisition and fast transfer. The components on this have to be space qualified. It's using a rad-hard processor. And the time it takes to qualify a processor is usually a decade. So we're always at least a decade behind the times there.
So but if you had sort of a super fast processor, super good cameras, all that kind of stuff, then in theory it would be faster than having the manual. Is that right? For the manual, there's all this latency and concern.
Well, yeah. So you're saying, well, couldn't it be faster if you actually had all the right sensing on board? And yes, you're absolutely right. If we had, there's a trade-off. Given a certain amount of drive time available per day, the current trade-off is driving with all the autonomy to avoid obstacles. Our best rate so far has been about 23 meters an hour. And driving blind, our best rate is 100 meters an hour. So if we could get the autonomous rate up to 100 meters an hour, there'd be a lot of incentive to use it. And so, we're looking at the next mission, deciding how we're going to do that. But generally, we don't make changes to stuff like that unless it's motivated by a science goal. So if the science team is telling us, we don't want to go any faster than you went on the last mission, we probably won't. So I would love to go faster, right? I'd love to be going even faster than the blind speed. Why not go faster? We've set the drive speeds so that we have enough torque to overcome obstacles. Each wheel has enough power that it can pull half the weight of the rover. So, motivated by that special case, they put the speed very low with a very high gear ratio. But you could imagine systems that were built differently. We just haven't had the incentive to do that yet. Okay, so you saw how the onboard autonomy works. The way we use it is we usually stop every half a meter to a meter and a half, taking 4 sets of images now, not just the one image pair, to follow that whole process. So here was an example of the first time that we used that software on Curiosity. Now, remember earlier on in the talk I showed you a drive that was 2 straight line segments, a little off to the side? That was the plan for this drive. And here you can see that when it drove, it didn't quite follow the plan. It didn't quite go in the straight segments. The first part was straight enough, and then here it did a little curve. And let me show you what ended up happening. These are the maps that it generated on board internally as it was driving. So it took pictures, processed the data, and it color codes the map, every cell on the map based on how safe it thinks it is. Green is really safe, go ahead. Yellow is, it's a little rough, but go ahead and drive there. Red just means don't go there. And so the reason you see red all around the outside is that the human drivers set a keep out box. We said, don't go to this area. If your position estimate tells you you're in this area, stop. We didn't mean for you to go there. It's a way of constraining it to not ever get out of the terrain we want it to go through. And what you can see over here is, it's a little hard to tell, but every one of these gray specks is an arrow. What we have on board is the ability to plan the best possible path to get to the goal. And so what it's doing is it's evaluating at every point, what's the next best step I can take to get to the goal. It's a global path planner. You may be familiar with A-star search. People use it in video games a lot for optimal course planning. At Carnegie Mellon University, they developed an optimized version of that for driving called dynamic A-star or D-star. And what it does is it is still an optimal A-star search, but when you have a map update that's tiny, like when you're driving and you just see a little bit of the terrain, it's very efficient. So it runs much faster than plain old A-star would run. It doesn't have to do the whole search at every step. And we have that software on board. So here's a view of what the rover actually did during the autonomous part of the drive. So it had gone this way, and it turned on its cameras, and it saw this stuff over here. And it's not that big. It's not so big that it's a real hazard it can't possibly go over with the wheels. But it still noticed that this part of the ground was flatter and even better than that. And given the weighting functions that we had on that first day, that was enough for it to choose to drive around the outside over here. We've since changed the weighting. We didn't want it to avoid the small rocks anymore, but that was the first day activity, and it worked just as we thought it would. So what else drives curiosity? A lot of challenges along the way. One interesting thing, as a roboticist, people tend to trust sensors more than the high-level autonomy processing. And that had been our experience in initial development, too, that in order to estimate where we are, what our attitude is, you really trust the IMU implicitly, right? And we all have smartphones now that have accelerometers and gyros in there, and you kind of trust it to do the right thing. So on this one day, it turned out that, and so one way we enforce that is we say if the vision system's estimate of what our attitude is differs from the IMU by more than a degree or whatever the parameter set to, then you don't trust the visual odometry, you trust the IMU. And so we got a fault on this day and on 2 days after that the Visodom disagreed with the IMU and like, what's going on? It's not supposed to be that far off. There must be something wrong with all the software. Well, it turned out that the Visodom was actually right. What was going on is that someone had set a parameter in the integrator for the IMU that would ignore gyro changes when there was a big acceleration. So if the acceleration is too big, they reason that must be a faulty reading, you should ignore it. But what was happening is we'd be driving, coming down off a rock, you'd hit an acceleration, and it was a big enough force that it met that threshold they had set, and it was just ignored. So the IMU estimate was actually off from reality, and it turned out to be off by what the visual odometry had measured. So this was a case of not finding broken software from the sensor, but finding the broken sensor with a broken high-level visual odometry software. So we updated that integration parameter, and we haven't had any other problems since. And it's been working really well for us. This was a few months ago, but as of then, out of 3,800 updates, we had only failed to produce an update twice with 2 frames. And that was because we were looking at terrain that was so sandy, there was no texture there. We couldn't find enough features autonomously to track it. Another problem we had last year was a flash problem. Rover found some problem with the flash memory and ended up rebooting, and the ops team decided to switch to the backup computer with backup flash in order to deal with it so they could assess it safely from the other CPU. And they did find a real problem, and they ended up deciding to disable half of the flash on the main computer. The RCE is Rover Compute Element. That's one CPU. So they disabled half of the flash on the A computer, and actually we've been on the B computer ever since. We haven't gone back to the A side. So that was a case where everything worked as it should. There was a problem, but the fault response acted correctly. It informed the team of the problem. The team reacted quickly to switch to the backup CPU, and everything was fine. We were able to resolve it and move on. Except for one thing. I mentioned earlier that the cameras are tied to the CPU. So when we switched CPU, we went from the top navigation cameras to the bottom navigation cameras. And when you do stereo vision, you want to have the cameras maintain their alignment. So between all the stereo pairs on the rover, we have like a titanium bar to keep them rigidly mounted with respect to each other. But if you notice, these cameras don't have a bar between them. They're sort of hanging down from the ones above. And what we noticed was that when we tried to do stereo with these images from these cameras, like stereo processing not with the eyes but with software, we weren't getting very good results. It was coming out really poorly, and it took us a while to figure out what was going on, but we eventually realized that the cameras were warping with the temperature, ambient temperature at Mars. That was a problem, but it turned out that it was actually predictable. You could model the warping based on the current temperature. So what we did was we actually had to write some new software, upload some new software to read the temperature sensor and update the camera models appropriately. And with that we were able to keep working again. We figured out the problem, we tested it on the ground. Once we had the right solution, we uploaded a version of that solution and kept it going. Later, we had a new version of flight software. We incorporated a more efficient patch to that directly into all the code instead of just a little quick fix. But happily, we got it working again, but it did take a few months to sort it out, to understand what was happening, get the solution, and get it on board. And you can actually see that reflected here. That happened on Sol 200. We had started drilling right before. This is the odometry of how far we went each Sol. You can see we didn't do a lot here. Here we were drilling. Here we had the fault. After about a month, we had a ground solution worked out that we could still fix the models on Earth with the right temperature. But then Mars went behind the sun for a month. So we couldn't do anything anyway. So we lost almost 100 sols here just because of drilling for not moving, and then the fault, and then solar conjunction. But you can see we've done pretty well driving ever since. So it's another challenge. One time so I mentioned when we do the autonomous driving, the rover's in charge, and usually we start the day with a human choosing how to drive. But if you have a weekend and people aren't working on the weekend, or if you have, for some other reason, you don't get to talk to it in between, couldn't you keep driving autonomously? Yes, you could, and we've done it. We commanded it successfully on Sol 435, and then we tried it again a few weeks later, and this time it failed. And what happened was we drove blind, and we got out to here and we started the autonomous driving. Now this was going to be a really cool autonomous drive. They had sequenced a plan to go like 200 meters more off the chart here. But what ended up happening is pretty much right away it saw something and tried to work its way around it. And you can see here what it saw. It's driving up and there's a little crater here. And the reason we couldn't see it is it's a little depression in the terrain. The end of what you can see in the blind cameras is where the depression starts. So in retrospect, it's kind of obvious that there would be something there. But it tried to go around it, but then I was talking too much. Let me bring this back up again. So here we are approaching the crater. It's going to see it and veer right. You can see it steering to the right there. And now it's going around the crater, around it. Eventually, it hits the end of the red box, that keep-in zone. The red zone is where you don't want to go. So even though it's finding a way around it, it says, oh, I'm hitting my red box. I can't go any farther. It turned around. You can see the tracks here. It's going back over its own tracks to go the other way. Now, this was especially interesting because we had actually set parameters to not let it drive backwards. So when we started seeing these backward tracks, it was a little concerning. It turned out that I had left one little hook in there. Of all the paths it could choose, almost all of them were forward, but there was like an optional choice if you're totally boxed in, but you can turn around 120 degrees, it was still allowed to do that. So it found that one option, backed into the corner, and just did a turn in place and started driving the other way. So the autonomy, took over, and emergent behavior took over, and it found a way to get out of the box we'd put it into. The drive ended up stopping for other reasons. It ended up stalling when it was steering one of the wheels, totally unrelated to the autonomy. But this was a fun day to figure out what happened when, it's confusing, it's driving backwards, and it stalls. Happily, everything just worked just fine, but it was a tough day to get the first images back and try and explain what happened. This is the map that it built up. You can see the edge of the crater here. It goes off to the side, gets boxed in, and then turns around and comes back the other way. So the other issue I mentioned is that we discovered that the wheels were getting torn up much more quickly than we expected. You can see here at the bottom, I guess it's a little dim, I'm sorry, but if you can see right here, that's a piece of the wheel that's been pushed inside. What ended up happening is we ended up in terrain that we had never experienced before. Sojourner didn't experience it, Opportunity, Spirit. We hadn't found terrain with rocks that are so embedded into the ground that they won't move out of the way when this big rover comes onto it. Normally in the past, when we'd seen small rocks, we would just push them into the ground, push them off to the side, they'd move out of the way, everything was fine. But here, the rocks weren't moving. And these wheels, these 50 centimeter diameter wheels, are machined out of a big block of aluminum down to the thickness of less than a millimeter on most of the wheel surface. That's like a tin can. And so you're running a tin can, you're pulling it against a rock that's not moving, and it just pokes right through. So we started noticing right about the time of that last drive that we were starting to get these problems in the wheels. Here's some before and after. When we landed, just 2 weeks after we landed, the wheels looked nice and pristine and good. And just 2 months later, we can already see little dings, but the dings didn't worry us. But almost a year later, it still wasn't that bad. We hadn't hit that terrain yet where it had those embedded rocks. We'd been in nicer terrain up to that point. Even here, there's more dents, but there's no punctures yet. So more than a year into the mission, we're still fine. But now, all of a sudden, it's getting worse, and we're starting to see actual holes in the skin on the wheels. So that gave us pause and made us slow down a lot and reassess our strategy. We had driven from here all the way down to here, and at this time was when we realized there was a problem with this terrain. So we asked the science team to help us understand what's going on. So they came back with this map where they said, green is pretty good terrain for the rover, yellow is this embedded stuff. And you can see we discovered it like right in the middle of the sea of yellow. So we couldn't back out. It was the same, just as bad as going forward to try and get out of it. So what we ended up doing was trying to change our course through here to try and micro-optimize every step to avoid that kind of terrain. But I actually found it really interesting that the science team, after the fact, could go back and reassess the data they already had and say, you know, from orbit, we can only see down to this resolution, but based on all the other features we see, we can predict that these tiny rocks that are only 2 centimeters tall are going to be a problem in these areas. And they were right. They were able to get that assessment right, even though they couldn't see the actual obstacles there. So we had another issue. The first time we encountered a big dune here, this was a dune they called Dingo Gap after a feature in Australia. This thing was about 1 meter tall, just a big sand pile, and this was the way out of that nasty terrain. So we'd been climbing in the nasty terrain over here, and we said, if we can just get over this, it gets much better. It's a much nicer terrain, but can we get over it? You know, we don't know. So as it turns out, we got up close and we studied it, and we looked at the slope, and the scientists told us that, you know, the slope is actually less than the angle of repose for this material, which means it's actually been there a while, it's weathered, so it's probably more compacted, it's probably able to support the weight. So we planned a drive to go over it, come over to the side here, get some of the wheels on some of the rocks on the side and some of the wheels on the sand. And that was the plan. And happily, it actually worked just fine. And what I did here is project the course that it took. We were driving in a straight line, and here's that sand wedge viewed from above. We're climbing over it and coming down to the other side. What you can see in this view of the course plot is the red data shows where the rover thought it was. So we were using the visual odometry to update its position knowledge, but it only runs every meter. So in between every meter, it thinks it's here, and then it gets a correction. You see this impulse jump back to where it was. So the green line is sort of the smoothed over view of the telemetry after the fact, but the rover itself thought it was doing the red drives here. But so happily, it only took 2 sols, 2 days to get over this thing. But there was a lot of concern and consternation whether we'd be able to make it, and happily we had no trouble whatsoever. I wish that had held true later, but at least here we were doing just fine getting over this thing. So it takes a while to do the whole playback. I can jump back to it if people would like later, but basically that was the end result. Looking back at our tracks, you can see we were able to climb over it, came down the other side, and there was slip along the way, but it wasn't that bad. It never exceeded more than, I think, 50% going up the other side. And this was fun for me. I get to be the driver both on the upside and the downside, or one of the drivers those days. So it was nice to see that everything worked out. So let me go back to this. These are the drive statistics for the whole mission in all the different modes that we were driving. So viewed this way, what you can see is that our top distance per sol was about 140 meters. And this ended maybe 4 months ago. We do have more since then, but it's a similar record. We're still at about 140 meters per sol. But I really like this view of it better, because here you can sort of see when we started using every behavior, and like just by the slope you can see when we were driving a lot and when we hit a problem. Here's where the wheel wear came into play, where we saw the holes in the wheels. We took some time to drive much more slowly to figure out what's going on, and then we eventually got a handle on it and got better. But so the red is where we drove in the directed way without using vision. This blue is where we drove with the visual odometry. So you can see we actually use that part of the autonomy a lot for the mission. That's every step, every meter, stopping to take pictures and measure your progress. The purple is the avoiding hazards mode of driving. And this green one is a mode sort of in between these two. It's where we used visual odometry only as we needed. So it would kick on every 20 meters or so to measure, to see if we got stuck yet, just as a slip check, as a sanity check. We'd like drive in the blind, stop, move a little bit, stop, and see if we were stuck. If we weren't stuck, drive another 20 meters without looking. But along those 20 meters, it would use other criteria to think about whether it was getting stuck. So we can check average currents in the wheels to see if that's going up too high. If it's increasing beyond a limit, then we'll halt. Well, we won't halt the drive. We'll do something else. But if that happens, if our tilt is too high, if we're turning but we're not turning fast enough, or if we know we're slipping because we measured slip, what it'll do is it'll kick on visual odometry automatically. So the autonomy will kick on more autonomy if it discovers that there's some reason to do that. And that mode was invented for Curiosity based on the Opportunity experience, because Opportunity got stuck unexpectedly, and only later, looking at the data, did we realize, well, if we had a filter on the average currents, that could have stopped us. If we had a filter on the turn rate, that could have stopped us. So all these things are now in the flight software for the new mission. Yes?
Where the correct answer to slippage or other faults is not to stop because stopping makes it worse?
Yeah, so could there be a case where stopping during slippage would make it worse? That is possible, but unfortunately in this architecture, we have to stop to collect the images to process, to determine whether we're slipping. So we don't actually have a choice in this system.
That says, okay, apply more power here.
No, there's no fault that says apply more power here. No. What we'd have to do is we'd have to reconfigure parameters to allow more current to be used, set the current limit higher. And we could write a sequence of commands to do that, but we haven't done that to this point. I'm just going to skip over the others. We have the numbers for tilt, pitch, roll, and yaw for the whole mission available for study. But I think, I'm running out of time here. I think I should wind it down, but just to show you some of the science results that we got. I mentioned before that they determined that where we landed was in the outflow of a previous water distribution network. And so they determined that by looking at and analyzing the mineral contents and things nearby. And this was something they didn't expect to find until we got all the way to the mountains over here, but we actually found it very close to the landing site, which is why we ended up staying near the landing site for most of the first year. We did drive all the way here. You can actually see tracks. This is an orbital picture showing the rover's tracks. So I mentioned before, we get like quarter meter resolution, so you can see the scale of it here. They really liked this location because it was the intersection of these 3 different kinds of terrain types. And that's where they got the evidence for the neutral density, or neutral pH water. And here they show that some of the rounded pebbles and sand indicate that the depth of the water was at least not trivial, not just a little small covering, but at least ankle to hip deep. So no, not necessarily an ocean, but at least a standing pool of water. And you can see just some of the terrain they found there, all kinds of interesting things to try not to drive over. And I'm not going to go through all of these in any great detail, but you can see some of the science instruments on the rover here. So we have the color cameras on the mast, a weather station, measure wind speed and I think barometric pressure. There's the DAN instrument, which sends out a neutron pulse to look for subsurface hydrogen. And they'll be running that as we're driving sometimes, or every 15 meters or so as we're driving. The APXS sensor for the chemistry of rocks on the turret, the close-up camera imager on the turret, and the different instruments we talked about before. SAM is the chemistry and isotope processing that requires a sample from the arm to go into the oven inside to be studied, and Chemin for mineralogy. So they've also measured, the RAD instrument measures the radiation flux, and so like they measure the radiation on the way to Mars as well as on the surface, and that's informing mission planning for eventual human missions to Mars. They wanted to know about the radiation environment. So I'm going to just skip through a little unless people have questions about a specific one, but that's the size of the oven inside the rover. That's one reason it had to be a big rover, was to just hold all the science instruments there. Yes?
There's an issue with the oven can only be used in times. I got the impression there was it had reagents or something that it had a limited capacity for, or a limited supply.
I'm sorry, you're asking about limited capacity or limited supply for which instrument?
For the oven.
Oh, for the oven. Oh. Yeah, I think right. There are a limited number of tubes that you can put samples into that can go into it, right. So there's a lot of limited resource components of some of the science instruments. And the drill bits too. We have limited drill bits, but we do have spare ones if we ever need them. So, here's a nice view of the ChemCam, the laser. This is the terrain before and after a laser blast. And what doesn't matter, it's not the hole that matters, it's the evaporation that happens after it's fired. They take the picture and they run it through a spectrometer. But what's really cool here is this is a drill hole. And you can see in the drill hole they were actually able to fire the laser into the hole they had drilled nearby.
Has the rover ever used the laser for personal defense?
It has never used a laser for any other purpose to my knowledge. But maybe I'm not at liberty to say, who knows. So the main science results have been that they did expect to find some evidence for some ancient river deposits, because you could see from orbit what looked like a delta, like a fan going in. But they've also found that from the mineralogy directly there that it's really not too acidic or too alkaline, low salinity, and so just really nice water. It's the best water we've proven that there used to be on the Martian surface. And so what else drives curiosity? Well, future discoveries await. We had driven up to here, and we were looking at different kinds of approaches. Actually, this is outdated now. Just today there was a press conference with a new map planning the future drives. But basically we're planning to go down past all this black sand into a region here that's going to get up the mountain Sharp over here, and you can get a nice panoramic view like this. These are the buttes in the area they call Murray Buttes, just the small mounds. The original plan had been to drive a little bit past them and go up through, but today they made an announcement that they're going to cut a little bit short. We're actually already in a new geologic unit. We've driven 9 kilometers and we're already into a new area that's more related to this mountain than to the area we've been in. So that happened over a month ago, but they just made the press release today. And so based on that, they've decided to, and based on the local analysis of the terrain, they've decided to change the overall strategic path a little bit. So they do expect to be doing more drilling nearby pretty soon. But eventually, the goal is to go up the hill with this extended mission and any future extended mission through the different units. And they're looking back in time at the Martian history through all these different units. So The farther up you go, the more interesting it gets with the different history that connects the dots all together. We don't have a drill that's big enough to go meters or kilometers into the ground. Instead, we have to rely on geology or meteors to expose the layers in the surfaces. And so that's why rovers like to climb up into craters or up mountains, is to find that exposed geology. So this is what's changed lately. It's no longer the expected path to go this way. They've cut it back a little shorter. I can actually show the image from today's conference, I think. I think it was here. Oh no, sorry, I brought up another view. Just to show you how useful the autonomous driving is. Yesterday we drove over a little ridge, just about 12 meters, but we couldn't see what was on the other side. Today we see this. This is what's on the other side. And this is a rock that's clearly at least the size of a wheel that we couldn't see from orbit. So even though we can resolve quarter-meter pixels, this one was not obvious from an orbital view. It's perfectly obvious here, but this is why we have the onboard autonomy to let us go farther safely without plowing into something that we might not have seen from orbit. So that concludes my talk. So thanks very much for coming, and we look forward to many more years of exploring different parts of Mars.
Well, I'm just a little confused at some of the timing. The charts that you showed seem to all end around 650 sols, something like that. But it's been years.
Oh, well, no. Sorry, you're asking about the timing. Why only 650 sols?
Yeah.
Well, the Curiosity rover has only been on Mars for 746 sols. It only landed in August of 2012. Opportunity has been on since 2004. Yeah. Right, so I was showing mostly Curiosity. I wasn't showing Opportunity here.
Yeah, but even, okay, so it's just missing the last couple months, I guess.
That's right, yeah.
Okay.
And we have new data. I didn't get into the slide package today. Sorry about that.
And the sol is a Mars day or Earth day?
Yeah, sorry, I should have explained. What is a sol? It's a Martian day. It's called a Martian solar day. Since it's about 40 minutes longer, I mentioned before that when we were working Mars time, it was a little bit longer. We measure time on Mars in terms of local solar time. And just to have a quick abbreviation for it, we made up the word sol, short for solar day.
How do you do timekeeping on Mars? Or do you do timekeeping on Mars?
How do we do timekeeping on Mars?
Does it matter what time it is? So how do you track that?
It does matter what time it is because you need sunlight. We actually don't like to drive until the motors are warm enough. So if we didn't have sunlight, we don't drive at night because the motors are so cool, we'd have to spend a lot of power heating them. So we do care about that, and we do measure time using Earth seconds. But there's more Earth seconds in a Martian day, so we just take that into account in all of the the flight software takes all that into account.
I guess I was curious. This is maybe an esoteric question, but how do you keep? If you just have a watch, it'll drift, especially after years. So I'm wondering, do you just have a very high quality, like an atomic standard there, or does it get synchronized periodically from satellites, or how does it stay synchronized?
So how do we deal with clock drift? And the way we deal with it is that humans are comparing its estimate of time to time on Earth. And so I don't know all the details of what the clock source is there, but I do know that we always return time tags and correlated components. And so people are monitoring that on Earth, and they will deliver updates to that, either to the spacecraft or to our own internal planning tools to make sure we stay in sync. But it is a problem. Actually, Opportunity is having a problem with that now. They may have to update the flight software because the time has drifted so much, more than they expected. They have to do a software update to compensate for it. Yeah.
So now that we know what you use as a reference in the time domain, in the spatial domain, when you're using the visual odometry, I can intuit how that would work in a relative sense, that you build a map as you move. But does the algorithm also incorporate global knowledge, like from the orbital information, so that you can nail that odometry down to features you have measured globally?
Yeah, that's a good question. So does visual odometry incorporate global information or orbital information to tie down its estimate? And really the answer is no. We don't do that on board. If we were really going to have operation modes where we had to drive autonomously for days or weeks, we would want to do something like that. I mean, there are capabilities for localizing yourself with respect to like huge terrain features like the mountain or the hill way kilometers away. We don't have those on board in the flight software because on the scale that we're driving, we haven't needed that level of precision. The way that we maintain our localization on board is that we kind of reset our position every, say, a few hundred meters. We send a command that says reset your position, increment your index, and that resets it to 000.
Okay, so the rover doesn't have a
Right.
global notion of spatial.
Right, the rover does not have a global
But when you get the data back from the rover, when you're processing it here, you then reference it to a global.
Yes, right.
By global, I mean Mars.
Yes, so we do reference it globally here on Earth, and so that's how we produce maps like this.
This is exactly what I was getting at.
Right.
Is how do you take that drifty data and bring it back to.
Right. So part of the operations team work is that after we drive any distance, we'll have these images with the navigation cameras. They will use that to relocalize. So they have the quarter-meter pixel orbital data, and then they compare that to the panorama you get at the end of the drive, and they say, oh, I thought it was here, but it's really over here. And that correction gets incorporated every day by the team.
At a layer of the control system that includes humans on Earth,
Exactly.
not down on the
Correct.
on the
Yes. Yeah, I mean, I can imagine software on board that could do that, but it would be, you require a lot of data for your map, and it would require extra time. So it just hadn't been a priority to have that capability. Yeah.
What kind of significant changes for the next rover are being informed by the stuff you've learned from this mission?
So what kind of changes are being considered for the next rover? Well, it's very early in the next rover's development. We are talking already about how we're going to build the next one. They have announced that there will be a 2020 rover, and they have announced even what the science instruments will be on it. They've made those selections public already. But the engineering team is just catching up now. That announcement was only made maybe a month or so ago. So we don't have all the requirements in place yet. But basically, we're considering what are the science goals for the next mission? How many samples do we want to collect? How far do we need to drive to accomplish the science goals? And so that's going to inform what choices we make, what gets improved. One thing is that we've only been able to collect 4 drill samples so far. It's not that we couldn't have done more, but it's that's what the science team wanted. They only asked us to stop and do the drilling 4 times. But the notion is it would be better if we could collect more samples more quickly. It takes many days sitting in one place to do the operation because you stop. Did you stop in a safe place? Or if you use the drill, you're going to shake yourself loose and fall away and rip the bit apart or rip the arm apart. That takes some time, and then once you choose the target, you try to preload on it and see if it's stable enough. We actually just about a month ago, we tried to drill a target. We preloaded on it, was fine. And then when we started drilling, the ground just cracked apart and halted the drill. And the science team, what's that?
Broke Mars.
We broke Mars, yeah. So the science team gave up on that. They just said, well, it's not stable enough. We don't want to risk breaking things in order to get this one sample. We'll take another sample somewhere else. So that's a human-in-the-loop process drags it out. So the more we can automate it, the better off we'll be. But it's going to take some potential, design changes to make it possible to do more automation there. Yeah.
It seems almost catch-22. I mean, if the science team is driving, saying, well, this is what we want, but they're kind of assuming what the capabilities currently are. I mean, if you could drive like 100 miles a day, they would probably ask for different things, right?
Yeah.
So is there like a wish list on both sides and you're both kind of pushing on each other? Or, I mean, how, do they say, oh, wow, if you, give us a list of things that we could potentially have and we'll tell you what we would love? Or,
right, so
I assume there's communication like that, but it seems really...
Yeah, so the question is, did the scientists and engineers work together to come up with the next set of requirements, or how does it go? So far, my experience is that unless it's a technology demonstration mission, it's really led by the science goals. And the team just doesn't want to take on the extra risk, the extra cost, the extra test time, the extra activities of integrating more capabilities than are strictly needed. So But I have to say that I'm sure it was helpful that prior to the Mars exploration rovers, Spirit and Opportunity, a lot of scientists who were on that mission came to JPL and went to other places to see demos in the technology program of what was possible. Because people were driving rovers then, and they were driving them even faster than the current systems are. And just seeing how the rovers could work, just seeing that they could drive up and what they could explore and where to put the cameras. And there was a lot of feedback in the technology development stage. But right now in the mission proposal stage, it's really led by science. It's motivated by the science goals, and that really determines how much technology gets on board. As a former robotics researcher, I would love to do more autonomous robotics on the next mission. If they call for that, I'd love to be a part of that. But it's not a tech demo mission, unfortunately, so we can't just push stuff into it. Yeah.
So when you say science goals, is the science are the science goals directed towards humans visiting there and human habitation there?
So are the science? Sorry.
So what are the other science goals?
Right. So what are the science goals of the mission, and are they including leading toward humans visiting Mars? I don't want to speak for the 2020 mission. I'm not on that mission full time, so I can't really address all the science requirements there. But historically, MER and Curiosity, the goal was to show ancient environments, show where there had been the possibility for habitable environments, where there used to be water. Look for the evidence of past life, maybe, or at least evidence of environments that could have supported past life. So that's been the overriding goal here. On Curiosity, as you saw with the radiation detector, that's something that was added to get a better handle on the potential environment for astronauts in the future. So we are getting bits and pieces toward the eventual human exploration. But it's not like we're laying the foundation. We're not setting the tracks for the train that the humans are going to use. We're exploring the science and exploring the environment to understand what we have to send next. But it has been mostly motivated by the historical science context rather than just laying the groundwork for the human explorers.
It seems like the speed of movement is a pretty limiting factor. I didn't get it. You said that there were plans for improving the ability to monitor the stereo cameras and so forth. Are there plans for that now with greater technology?
So are there plans to improve the speed and improve the cameras to make it be able to go faster?
Yeah, for your autonomous driving mode.
Right, for the autonomous mode. I like the way you think. Yeah, I would love to go faster. And so I'm actually working with the 2020 team now. We're doing a study on what's the best way to place the cameras for the next mission to make it better for the autonomous driving and the blind driving. I'm not sure we'll get the telescopic mast in there, but we can mention it. So.
Or would it be possible to fly a drone?
To fly?
Yeah.
Like an autonomous quadcopter?
Would it be possible to have an autonomous quadcopter? Anything's possible. I've seen proposals for that, but there's nothing currently accepted for the mission.
Power limitation for that?
Is there a power limitation?
Power limitation because you have enough solar and it's dimmer there?
Well, I mean, you're right. There's less sunlight at Mars, so you get less power from solar panels. But it is possible, at least, to imagine something being built. You can get a lightweight quadcopter that can get enough power, and it doesn't have to fly all the time. It can fly just briefly during a day. It wouldn't need that much. So it is possible, and people are looking into proposals, but there's nothing currently on the books for the next mission.
Maybe a drone that goes out ahead of it, comes back, and just to give you a better stereo view.
Yeah, you're right. It would having such a thing would give us a better view of the terrain, and one of the limiting factors on this directed drive distance is how much you can see. So if we could have something that would give us a view of the terrain ahead, that would open up the possibility of more directed driving and faster driving that way. Yeah.
Are you limited by computing capability on the rover itself?
Yeah, are we limited by computing capability? Yes, we are. The vision processing that we do is detailed enough that we are CPU bound for that part of the processing. So it does take tens of seconds to do all the visual odometry and even longer to do the hazard avoidance because we're taking 4 stereo pairs along the way. So there are other options. You could imagine having FPGAs or another kind of coprocessor that would help speed that up. But again, that's more parts, more stuff on the vehicle the mission's not going to sign up to that unless there's a need from the science side that motivates it.
Is there any chance of maybe offloading that to an orbiter or something?
Any chance of offloading computation to an orbiter? Well, there's always a chance, but at present, the orbiters are really in low orbits, so they're only really overhead for a brief period. When we send data back through the orbiters, we only get a few minutes to send all the data in a burst. So I don't think that with current orbiters that would be a useful enough system. If you had something that's in a stable orbit that's always there that had better computing, I could imagine that. Yeah.
Would be bounded by heat, dissipation of the heat generated by computation.
Oh, are we bounded by heat? Yeah, we are. Part of the power modeling takes heat, and there's thermal modeling too, takes heat into account. And sometimes we have actually had to terminate drives because we're using the cameras too much. And the heat model predicts it'll go above the guaranteed range.
Put a finer point on that. Is the limit available energy or heat budget, or is the limit the fact that you bought the CPU 15 years before you launched it?
So is the limit on computing?
If you could send new hardware there this month, well, 6 months, is the problem that you had to build it with a 2000, year 2000 processor, and if you use modern hardware, would you get a free order of magnitude, or is the modern hardware not a whole lot better off because of power and heat limitations?
Okay, so the question is, are we bottlenecked in processor performance by heat or just by the fact that it's old, by history? As far as I know, it's not the thermal consideration that's stopping the processor from being used more quickly. I think it is just the fact that it takes a decade to space qualify a processor. So, we're up to 133 megahertz. The same board allegedly could run at 200 megahertz. There have even been, research studies or proposals years ago that say, just fly a commercial CPU, 4 gigahertz CPU, and it's going to reset because you're just going to get these radiation hits, but so what? You're on the surface, you're safe, you'll stop and reboot, maybe even a few times a day, but I would much rather have 2 gigahertz for 3 hours, except for the 10 minutes it's rebooting, than yeah, right. That's the thing.
When the 2 gigahertz one goes belly up, then you keep flying on the one.
Right. Yeah, you fly both, and so the thing is, right now we're using the same computer that had to be qualified for the entry, descent, and landing. So the approach to Mars, landing on Mars, is super critical. There's only one shot at it. Earth can't possibly communicate with it during that time. You may have seen the video 7 minutes of terror. If it takes 8 minutes round trip at best, in 7 minutes it's all done. You don't have any impact on it. So we're using computing that was designed to meet those requirements, that it had to survive coming into the atmosphere at high temperature, slowing down, and mission critical stuff. When we're on the surface operating in a slow drive mode, it's really not the same kind of risk to the vehicle. So, there is the potential for using other kinds of solutions there. All right, well, thanks for coming.